My name is Laura Young. Welcome to the Hawaii Department of Transportation's 2025 Protect Our Water Conference. I will be your moderator for this morning's session titled Sustainability and Shoreline Restoration for Highway and Port Projects. At the end of the presentation, the speaker will have a few minutes to answer your questions. So without further ado, I would like to introduce our speaker for this session. Richard Price is a professional engineer with 31 years of experience in design, construction, environmental compliance, low impact and sustainable design, and climate change issues, working for clients including ports, federal, state and local governments, and private industries. His recent work has focused on greenhouse gas reduction planning, as well as sustainability and resilience to sea level rise. In addition to his professional environmental consulting experience, Mr. Price has lived and worked in Nepal and the former Soviet Union, where he worked within the United Nations system, constructing irrigation systems and developing economically and environmentally sustainable housing, water supply, and sanitation facilities for refugees. At EA Engineering, Dr. Mike Foley focuses on nature-based solutions for coastal resiliency. Over his 19-year career of addressing natural hazard risks in Hawaii, Mike has remained fascinated by the concept that hydraulic design may not only address infrastructure challenges, but can also promote valuable ecosystem services such as wildlife habitat, flood attenuation, water quality, recreation, and cultural uses. As a professional engineer, Mike has experience in shoreline erosion, harbor protection, flood risk mitigation, repair of coastal structures, hydrology and hydraulic evaluations, dam adaptation, dredging, beneficial use of dredge materials, beach nourishment, living shorelines, and coastal dune restoration. He is passionate about preserving our coastal ecosystems, including beaches, dunes, wetlands, and coral reefs, and volunteers in his community with various nonprofits organized around this goal. So please help me in welcoming Richard Price and Dr. Mike Foley. Good morning, Richard and Mike.
Thank you, and good morning, everyone. It's nice to see so many familiar faces, and for those of you I haven't met, I'm Richard Price. I've been working with Highway O on their stormwater program since 2009, so it seems like a long time these days. I'm going to jump right in because we're going to try and cover a lot of information here. I'm going to talk a little bit about greenhouse gas reduction planning and a little bit about sea level rise and vulnerability assessments of infrastructure. And then I'm going to turn it over to Mike, who's got the good picture, so you'll want to get to that. Just real quickly, for those of you who haven't worked in the greenhouse gas realm, they tend to divide it up into what they call scope 1, 2, and 3, and it has to do with how much control you have over it. You know, my car, I can decide how much I'm going to drive it and whether I'm going to buy renewable fuel for it or I'm going to replace it with an electric car. And then that's a scope 1. Scope 2, you know, I have to buy my electricity from the electric company, and so I don't have as much control over their emissions. In the mainland now, more and more states, you do have an option. You can buy green energy. You can choose the source of your energy. So there's becoming more flexibility there, but you still don't have complete control over it. And then scope 3 is things that other people do. When Amazon delivers your package, you don't have control over what vehicle they use to deliver it in. So you really can't control it short of not ordering everything from Amazon. I'm going to talk a little bit of a case study. This is some data from the Port of Seattle. And they put together a plan to manage the emissions that they control. And so you see the bubble on the left there is the things that they're working to reduce. The biggest chunk of it being energy for buildings and facilities, for heating and lighting and that kind of thing. And then you see their fleet is their vehicles and equipment, and employee commute is a big chunk of it. But when you look at that bubble you see the little wedge is only 4% of the greenhouse gas emissions related to the port. And that's not even counting the ships travel all the way across the ocean. That's just the ship's time within like the Puget Sound area. So you're seeing this at a lot of organizations. They're putting a lot of effort and a lot of money into controlling that one little wedge, and there's a whole lot more work to be done for all of us. And then I just wanted to touch on a couple of ideas to show you how quickly this is all changing. We put this plan together in 2019 originally. And then, of course, COVID happened, so you see the little dot there for 2020 emissions. Things can change really quickly. But also, if you look over, you're seeing the business as usual line that continues to go up because we all want to grow and do more of whatever it is we're doing. But the goal stays fixed, so it gets more and more difficult to make those reductions with time. And the light blue wedge you see at the bottom there was their plan to replace all of their natural gas heating with electric heating that would hopefully be green electricity. And then in 2021, I believe, they signed a long-term contract for renewable natural gas. And that whole wedge goes away as long as they have a supply of renewable natural gas. And so suddenly, as you're prioritizing what order are we going to do all these things in, the landscape is changing so fast. The technology is moving, the opportunities that you have. So it is a constantly changing process. There's another quick one, the employee commute, which they kind of just had as a gradual reduction as we get people into electric cars and we're able to get people to carpool and take the bus and whatever. And again, you see 2020, they met their goal. Of course, since then it's rebounded somewhat, but with the hybrid work model, was never envisioned really in the planning they did in 2019. So these things can change quickly on you as you go. And I put this slide in real quickly because this is the maritime activity, the ships and the activities that maybe the port doesn't have as much control over. And I think it's interesting because if you look at the numbers, they started at about 120,000 metric tons. And on these, we're talking about starting at 1,000 or 1,400. So it's an order of magnitude bigger, the issue that's still hanging out there, and about half of that is not really, they don't have a plan of how we're going to power container ships without any emissions. So something to think about. And then this is just an interesting slide. This is fairly old. McKinsey did this report in 2007, but it was talking about the different things we can do to eliminate or reduce emissions. And you start out with the green ones, and this is the stuff that actually saves you money, right? We're all replacing our light bulbs with LED light bulbs that use a lot less electricity, and so it's a no-brainer. Why wouldn't you do that? It's going to save you money and reduce emissions, and it's good for everybody. And kind of the same thing with, buying an electric car. You don't spend as much money on fuel. You don't spend as much money on maintenance. In the long term, as prices continue to come down, electric cars we're going to be driving them anyway, not necessarily just for the emissions, but just because they're cheaper. And then as you move to the right, you get to some of the things in the middle where it's maybe a break even, or you have to, spend a little bit more. We've got to develop new technologies. We've got to work more. And then obviously when we start trying to get to the harder things, they're going to cost more, and we're going to have to work harder for it. And I'm not going to go into the details of all these things, but something to think about as we move down the road with this. And then I want to shift gears a little bit and talk about sea level rise and the impact on shoreline infrastructure. I don't know how many of you have seen this graph or something similar to it before. There's a lot of different projections of what we think sea level rise might be. somewhat dependent upon how much CO2 we can stop putting into the atmosphere. But if you look at even the low estimate is almost a foot rise by 2100. And I don't know how many of you have been to the beach on a king tide day and seen the water. I think there's a king tide in a couple of weeks. Yeah, the first week in December. You'll have to be one of those early risers that goes for a walk at 5 a.m. I think, but we're due for one here. But you know, a foot above where those tides are, and we're going to start seeing significant impacts. And obviously, with the high number here is almost 7 feet, so that won't even be an issue. Everything will be underwater. But most organizations are looking at sort of that intermediate or the intermediate high in their planning work, because it seems to be maybe the most likely scenario, or at least the planning for it might be achievable. So that's kind of the range that most organizations are looking at. And I'm going to do a quick dive through a whole bunch of information about the Port of Bellingham and a infrastructure vulnerability assessment we did for them. But it basically takes in, you know, what we know about the water there. We used a Cosmos model, and I'll talk a little bit more about that from the USGS. We went out and got GPS elevation data for a lot of their shoreline infrastructure, bulkheads, stormwater catch basins, fuel islands, a lot of the stuff that was, you know, on the waterfront or near the water line, and then some of FEMA's flood data as well, and put that all into GIS and produce some images out of it. The Cosmos models is the coastal storm modeling system that USGS has put together, and it takes into account the sea level rise, the tide conditions, and then the wave wash up, because during a storm you might have 2-foot waves, but the water can actually come further up the beach than a 2-foot wave would, because all of the water is being pushed up, and so the surface of the water actually rises up towards the shore. And so it takes all that in. They are still working on this model, and they're going to start incorporating like inputs from a stream or a river that's coming in, because that also raises the local water level to incorporate that. But I'm just going to run through a series of pictures here. This is so this is the king tide scenarios. This is with no storm event, and the dark blue is today, you can say, with no sea level rise. Then the orange, I believe, is about a 1/4 foot, or it's a 1/4 meter, so about a little under a foot. And then the light blue is our 1 meter sea level rise, which is sort of getting to that moderate prediction level that I was looking at, kind of a 3-foot, little over 3-foot sea level rise. And at our king tide scenarios, you can see at the, you know, now they have a few little localized issues, not dissimilar from what Honolulu is facing. But by the time we get to the 3 feet of sea level rise, you have whole portions of the facility that are going underwater. You know, maybe a few inches is not a problem, but when you get more, and it depends on what the infrastructure is there. And then we add in a 10-year storm, and you can see all the colors go up, and a 25-year storm, excuse me, this is a 50-year storm. I skipped 25. And then the 100-year storm. And you can see with the 100-year storm, the dark blue is impacting even more of the sort of the edges of their property. But even at, you know, less than a foot sea level rise, the pink, you're starting to see significant encroachment on some of their facilities. So like I said, we then took this data and looked at specific infrastructure and how deep it's going to be, how deep the water is going to be over that catch basin or that electric gate opener or whatever the infrastructure that we're concerned about. And we did a sort of a low, medium, high ranking of all of their infrastructure based on kind of the amount of sea level rise required, as well as the intensity of the storm that would be required to inundate that infrastructure, and use this ranking, and then incorporated that into maps to show, okay, well, these are the parts of your facility that you probably want to focus on first. We want to go look at this specific area. And we then expanded that, and so that map that you just looked at is what would be exposure in that first column, and the high, medium, low ranking for that. And then the sensitivity and the adaptive capacity. The sensitivity is how much is that item going to be damaged. If you have a warehouse that floods and it's got a concrete floor and the electrical system is all elevated off the ground and you get a foot of water in the warehouse, you can sweep it out and go back to work. If you have an office building that floods even an inch deep, you've got all the carpet, you've got the drywall is going to wick water up into it, and you have a much bigger, it's much more sensitive to the impact. And then the adaptive capacity is how easily can you change that. If you've got a parking lot that looks like it's going to be subject to flooding, it's pretty easy to decide, oh, well, there's a big storm coming. Let's not park any of our equipment in that parking lot tonight. That's fairly easy to adjust as compared to something that's built in and bolted down there that you can't do anything about in a relatively short time, and maybe that has to be in that location. You can't relocate it. So with that, I'm going to ask Mike to come up and show you some pretty pictures and talk about how we can protect the shoreline.
Thank you, Richard. Aloha, everyone. What a pleasure to be here with you all. So I'm Mike Foley. I'll talk about living shorelines for coastal resiliency and engineering with nature and how that relates to protecting our water. So what are living shorelines? So first of all, a living shoreline, it's a nature-based method for stabilizing the shoreline and protecting it from erosion. And nature-based is an important term to consider because ultimately that means understanding natural systems and the way nature on its own protects shorelines from erosion. And so to understand living shorelines, you really got to kind of start with thinking about the natural system. And here we are in Hawaii. The natural systems are a little different than on the continent, but this term definitely, or this idea definitely applies here to Hawaii as well. And so I'll show you in this presentation some examples of living shorelines in Hawaii, but also some that have been constructed in the continent. So when we look at this image, of course we see a beautiful watershed, we see a beautiful coastal ecosystem and a thriving coral reef. Those components are all important parts to a living shoreline. And I would argue that a living shoreline is actually one of our most important pieces of natural infrastructure for protecting our society from the impacts of sea level rise, as Richard was showing just how bad things can get. And it's really a system that works in balance with nature, and that's when it works the best. I'll get into some of the details, but I wanted to just highlight some of the benefits of a living shoreline. There's a lot. First of all, purifying and filtering water. And that's a perfect topic for today because ultimately that's what we're trying to do and that's what we're here about. So we can store floodwater in living shorelines before it gets to the ocean. We can also store carbon as it relates to climate change. And we can buffer that storm surge, that flooding, that overtopping, those wave run-up that Richard was talking about, living shorelines can buffer that impact before it hits our communities. Of course, we can reduce erosion, and we all know erosion is a huge issue in Hawaii. We're losing beaches, we're losing highways to erosion. And many people probably don't realize this, but living shorelines can outperform some of your traditional hardened shoreline techniques. And that's because these natural systems, they grow in time, and they actually can grow more stable as vegetation and ecosystems establish. These shorelines are resilient against storm impacts, whereas some of our aging infrastructure, our old seawalls, are not, and you're seeing seawalls collapsing left and right. And another great benefit is habitat for our wildlife, our endangered species, our protected species, but also for our people. So culturally, shorelines are important. And they also provide recreational benefits to the beach users, the ocean users, the fishers, the surfers out there. And it's also an important part of our tourist economy. People come to Hawaii for our beaches, for our shorelines. So let's look at kind of this graphic. I had some fun putting this together. Got a little moment to get a little artsy, so bear with me. But this is what a living shoreline is. So it is a part of our overall hydraulic system. It's an important part of protecting our waters. And the reason is a living shoreline is, so it's kind of that orange area represented by a bunch of sand along the shoreline. A living shoreline works in balance with the coastal forces of the ocean, but also the forces of the watershed bringing down that flow. And it can store that flow behind the sand berm, behind the dunes, and filter that stormwater before it enters the ocean. So naturally you'll see coastal wetlands in undeveloped areas, and those types of features are things that I would argue that we need to bring back. We need to bring back that initial storage of that storm flow from those rain events behind living shorelines. And living shorelines, they don't work in a vacuum. The reason that we have sand dunes, that we have these types of berm features, are because of our thriving coral reef ecosystem. So the reefs produce the sand. That's why our sandy beaches are white and not black lava. The coral reefs produce the sand, and that natural ecosystem works with the habitat that the reef creates. So it's a symbiosis. It's the fish that live on that reef, that are nibbling on the reef, that are creating the sand. It's also the waves that break on that reef that are eroding some of that feature and then pushing that sand up to the shoreline to create the beaches, to create the dunes, and also the winds that then blow those sand particles over the beach and start to form dunes. And the way that works is the vegetation that grows out of the dune, when those sand particles get transported by the winds, they collide with the blades of grass, the vines that are on the surface of these sandy features, and they fall to the surface where the winds are lighter because of that protection, and so they can stick there. They can, if there's no vegetation, they can also blow to the leeward side of the dune where the winds are light, and they can fall out. So that's just some of the important kind of dynamics that are occurring along a living shoreline. Now, this is what I would argue a lot of the shorelines that we see around Hawaii today are in this condition, what I would call a dying shoreline. So this condition is where the dunes and the beaches are eroded, they're depleted, either due to natural imbalances in our system or to man-made impacts. And so a lot of times now we have runoff that just blows out directly past any sort of dune or berms and goes right out to the ocean, where it's bringing those contaminants to the coastal ecosystem. That's not good for coral reefs. Coral reefs start dying off. An important study just came out this year from Arizona State University, which showed that we need over a quarter of our reefs to be covered in living coral in order for our reefs not to erode. So think about that. We need corals on our reefs to keep our reefs the way they are today. I would say, definitely the data shows this, and if you're a diver, you would probably realize this over just maybe a decade of diving, that the reefs are dying. And there's not a lot of coral coverage out there. There's not a lot of fish anymore. And so that imbalance leads to an eroding reef system. And as that reef erodes, the water level gets relatively deeper. And that's important because waves break due to the ratio of the wave height to the water depth. And so as depth gets deeper, reefs get less effective at breaking wave energy on the crest of the reef, and so that wave energy just passed right over the reef and collides with our shoreline. And that causes further erosion and just leads to a negative feedback loop. So, living shorelines are part of the solution. Water quality, of course, is a big issue, and living shorelines can help improve that water quality before it gets out to the sea. So I'll talk about, or I'll show you some examples of actually constructed projects, but there's a range, they call it kind of a green to gray spectrum here of what a living shoreline can be. On the far end, on the green spectrum, we're restoring the sediment material, the sand along a shoreline, in the case of like a high energy shoreline like a lot of ours in Hawaii. We're storing that sand berm, that sand dune feature, and vegetation. You need that vegetation, right, to help capture the sand. Now, that might not work in a lot of cases because we have energy coming from the ocean. That might erode that vegetation, make it hard for that vegetation to stick. So there's different ways to mitigate the wave energy and keep that vegetation thriving along our shorelines. And so moving down the spectrum here, we can see a natural technique of edging, where you're using like logs pinned to the shoreline to help buffer that wave energy. Sills are basically low crested structures that provide more structural support to the shoreline, hold that sediment in place, buffer that wave energy, but also provide habitat for marine life, for things like corals or fish. Breakwaters are another technique. This is filtering the wave energy before it gets to the shoreline with offshore structures that help to disperse some of that energy, but importantly, let a portion of it through. That's enough to use that wave energy to push sediments up against our beaches and keep it there. Revetments are a more extreme condition where you have a lot of wave energy that you have to help mitigate. Revetments can become living shorelines if they're designed to be dynamic, where they don't use all the same size boulders, but use a range of materials from big boulders to smaller stones, and then incorporate vegetation within them so that they also become living features with habitat. And at the far end are seawalls. Seawalls don't always have to be just these vertical structures. They can also be designed to include vegetation and to be low crested enough so that when you do have larger storm events, that waves can overtop that seawall safely and push sediments into the shore area. So let me just show you some examples, and I'll try to leave a few minutes for questions. So this is a project just constructed this summer at Moku'olo'e, Coconut Island in Kaneohe. Here we are, Kaneohe. And so this is an example. On that far end of the gray spectrum, we're using a product here that's designed for habitat to create sort of that gray protection where the wave wash zone is. But at the top of this wall, we also, or this sloping structure, we also have a berm that's vegetated with some of our native coral or native dune species of plants that are on some of our tables. So these plants, these vines will eventually grow and cover over the concrete, and everything will look a lot nicer in the future. This is an example, a project that I helped lead while I was at Oceanet. So some of our friends from Oceanet are here, but this one is a beach restoration that was done on Kauai. You can see how depleted the beach was. Basically disappeared. We had a erosion escarpment approaching a 3-story building, and the solution here was to restore that beach using beneficial use of dredge material, and restore a coastal berm and plant it again with our native coastal plants. Now, looking at an example from the continent, this is an eroding shoreline in a more protected area. The solution was to build one of these sill structures, these low-crested sills that also then helped to stabilize the marsh that was restored landward of that sill. Now, living shorelines don't always have to be don't always have to involve structure like I showed in those first examples. In this case, we just looked at an existing shoreline here in Waimanalo, and this shoreline was being choked out by a bunch of invasive species. Ironwoods are actually pretty terrible for the dune ecosystem, so this was a project of removing the invasive ironwoods and then restoring the coastal plants that are beneficial for, again, capturing that sand, helping to retain the sediments that naturally belong in that coastal berm. And this project was led by Tyler, who's here with EA with us. Another example from the continent, shooting back overseas. This is a breakwater. This is an example of kind of those dynamic types of structures using smaller stones and a range of stones. So the bigger stones where you really need it, but the smaller stones where you don't. And so this breakwater is just helping to stabilize a natural vegetated shoreline and keep that shoreline from eroding. So working with what we have in this condition, but just providing some structural modification. And finally, this example here, also from the East Coast, this shows some of the more innovative types of habitat structures that are available now on the market for living shorelines. 2 examples of different types of designs that are designed to emulate some of the natural features that provide habitat for fish and for, in this case, oysters, but are meant to help that ecosystem to build and thrive in time, and to then as these things grow and calcify, they start to stabilize the shoreline even further and these structures even further. So with that, let me turn it over back to Richard.
I think some of you who saw me speak here last year, we talked a little bit about the 6-ppd, the tire additive that's killing salmon in Washington, and I had some new data on that. So, but in the interest of time, let's move on to Q&A, and if anyone has questions, we'd be happy to take them now. Here, both of our contacts are on the slide here if you think of a question later.